Thank you very much. I want to thank Daniel for and all the organizers for the very kind invitation. Actually, it's been really fun to be back in Bonn. I was participating in the master program a few years ago, and I have very fond memories. So it's really nice. And yes, so actually I have something in brackets because I'm going to talk about the full title for the first 2/3 of the talk, and then I'm going to remove one of the words. I hope that that removal makes sense, or I can actually convince you that it's not such a bad idea. So, first off, this is going to be fun. Credit to those people who credit is due. This is work that has been done over the last 3 or 4 years with several people. Frederic Valentin is one of my main collaborators in Brazil. If you realize this is essentially a Brazilian armada, Larissa Martins, who is in the audience, and she's from LNCC as well, the Laboratorio Nacional de Computación Científica in Petrópolis, but she has been enjoying. She thought that the weather in Brazil was overwhelmingly hot, so she came to Scotland for a year, and she has been enjoying the tropical weather in actually, so she's very happy about it. Diego Paredes, who is in Concepción, Chile at the moment, but moving back to LNCC in January. So again, somebody from the same. Tadeo Gomez, Wesley Pereira, who's now in Denver in the US, and Fabrice Jaillet from Lyon. So I'm not going to. I'm going to spend actually most of my time talking about the introduction, and what I mean by a characterization of the exact solution is nothing but a new weak or an equivalent weak formulation for the problem. And then I'm going to go straight to what the actual finite element method looks like. And this is going to be most of the talk actually. And then I'm going to open 2 different branches of this work. Something that we've done very recently with the post-processing leading naturally to a posteriori estimator. And then I'm going to remove the second M in the MHM method, and I will try to explain that. So, this is I'm going to be dealing with the whole talk with equations such as this one. I'm not going to convince you that that is of interest, especially if A has some multiscale features. I'm just going to essentially be very lazy and refer to all of the excellent talks we've had this week. And I'm just supposing that a symmetric and positive definite, uniformly elliptic, etc. Right? And the key point about the construction of this finite element method is the fact that we start from a hybrid formulation. So the first step in a hybrid formulation is, as always, you cut your domain in a collection of bounded open sets. Traditionally, these are simplices or quads. We, a few years ago, realized that extending these to general polygonal shapes actually doesn't make much difference. So we spent some time justifying that inside. And we break the continuity of U. We don't consider that U is H1 in the whole domain. So we relax the continuity and we seek for a hybrid formulation. So we test with a function that is not H1 in the whole domain, but H1 of each one of these polygonal domains. I mean, these polygonal domains can be fairly arbitrarily shaped. We need them to be decent. Okay, don't bring me a snake that is biting its own tail, please, or something weird. Some sort of star shapeness, some sort of shape regularity is what we need. Right, so we test against functions which are piecewise H1. We integrate by parts. Yes. So we integrate by parts, and these terms that usually disappear and do not longer disappear because actually V is not continuous. And as a good hybrid formulation, this is not considered the weak form. We introduce a Lagrange multiplier. So our unknowns are now U, which is piecewise H1, and lambda, which is an unknown that lives on the skeleton. That is the normal flux. Okay, that's a hybrid formulation that goes very, very far back. but now I added one unknown, so I have two unknowns and one equation, so I need to close this system, and the way to close it is imposing the continuity of U weakly. So this is a hybrid formulation all the way back to Gabriel in the 1970s, actually. And this phase we will be back. We need to keep it in mind. Lambda is essentially the technical definition is normal places of the H diff functions, but you can think of it as H minus 1 of the scalar, H minus 1 half of the scalar. Okay. Now, this, as I said, this weak formulation has been analyzed in textbooks actually, but what we do now is what we do when we can come from the world of variational multiscale methods. We do static condensation, right? So we write one of the unknowns in terms of the other, and we replace the result in the first equation with the static condensation. Hybridization, as it's been called in the mixed and hybrid finite element method world. And so for that we need to solve, essentially we do this locally. We, let me go back. We test these with functions that belong to each one of those polygons, 0 elsewhere. So we get our logger problem. We pass the Lagrange multiplier to the right, and we say, if I manage to write u in terms of lambda and f and replace it in the other equation, I have only an equation for lambda. And that would be great. But the only issue is that when we localize this problem, due to the operator we have, we generate a kernel. So the equation is well posed in the whole domain, but not locally, because, of course, there is a constant part of u that will never be reproduced by lambda, right? That's the point. So we can actually, it's a little bit more complicated, so we decompose u as a constant term, which is essentially the kernel of that bilinear form. That's not an elliptic bilinear form in the whole of H1. And plus two things. One thing that depends on lambda, which is the solution to the local problems, and one thing that depends on f. Don't worry about the part that depends on f, is essentially everything is encoded in this local problem, which I will write here, because I'm going to be referring to this later. So this local problem, which many of you, not you, T of lambda, k equals mono minus lambda v. And the test functions are in h1 of k with zeroing value for well posed. Okay, that's absolutely fine. So that problem is well posed. And I can write u as a constant per polygon plus the solution to a local problem with Neumann boundary conditions plus something depending on the right hand side. That is essentially, if you understand this, the second variable.
That's a typo, isn't it? It's a gradient t in this.
There is a typo. Yeah, of course you were going to pick up on the typo. No, thank you. That's my mistake. Did I write it right here? I wrote it okay here. Thank you for that, of course. So now we take this representation and we plug it in the other equation. I mean, we're solving a 2x2 system. So we plug it here and we end up with this equation, right? Which is an equation that all the action takes place on the skeleton of the domain. I'm still trailing this constant part. So this constant part needs to be fixed by what this problem didn't see, right? So at the end of the day, we have two unknowns. The Lagrange multiplier, which is the normal flux on the skeleton, and the one part that the local solves could not resolve, which is the kernel. Okay? So normal fluxes on the skeleton, and one constant element, cos mesh element. And to evaluate this, we need to solve another problem, which requires the evaluation of this operator, which is a solution to a local problem. Okay? So this is very, I mean, you all have seen problems like this. I assume that this is the equivalent weak formulation. This is the way at least I like to think about this method. So this is the weak form. What I did was essentially, what in the work I was involved, was to take this equation that was written not in exactly this form, but in a very related form in the original paper by Adolfo Araya, Chris Hausdorff, Diego Paredes, and Federico Lantan in 2013. And together with Diego, Federico, and Fabrice Jaillet, we took this and we reproved what you have to reprove for a mixed problem, which is an insert condition on this bilinear form, and the fact that the bilinear form A here is elliptic in the kernel of B, right? So that was proven back in the day by Frederic, and we polished it a little bit. We refined a couple of arguments, and we extended it to polygonal shapes, but actually the extension to polygons is not the most challenging part of that. That's essentially just reading carefully things, reading things carefully. Okay, so that's the weak formulation. And now we take this mixed problem, this hybrid mixed formulation, and we discretize it. And to discretize it, of course, we need two discrete objects. We need to define a mesh of the skeleton, which is going to be the mesh associated to the Lagrange multiplier. That's fine. And we also need a mesh that is inside to compute, to approximate the local operators T. Okay? So we need a space for to approximate the Lagrange multiplier, which is defined in this mesh of the skeleton, and we need a space to solve these local problems. And we decide to have discontinuous elements on this of degree L and continuous elements of degree K or K plus 1 inside, and the relationship between L and K plus 1 is not to go. Rule of thumb, the second level mesh needs to be fine enough with respect to this one, so there are enough degrees of freedom inside. Okay? I'm going to refrain to this, but it's not a complicated thing to understand once you get your head around it. But we need that the space in the submesh generates enough phase bubbles to be able to build a four-ton operator, actually. And with those ingredients, we write the equivalent version of the discrete equivalents of these local problems, and we write our fully discrete, now multiscale hybrid mixed method, which is find this discrete Lagrange multiplier in the skeleton and the one constant per element which was in the kernel, and this is our mixed problem. And what we can prove is, again, under appropriate conditions, the subcondition is fairly simple. This is not the difficult one because the space, there are many, the key point is that there are many more edges than elements. Okay, so essentially the subcondition is not complicated. This one is a little bit more tricky because we need that the second level mesh needs to be fine enough with respect to the mesh of the Lagrange multiplier, so for us to be able to build that for operator. And in turn, that tells us that we have an invertibility, we have a stability, ellipticity, I cannot find my words anymore, in the kernel of the bilinear form. Okay? So, once we realize that, we can prove optimal order estimates using a standard theory of mixed problems, but for a very particular mixed problem. For this mixed problem that, for its implementation, requires solving local problems and generate multiscale basis functions. This is a very, this is not a rough error analysis, but this is an error analysis where we have just assumed that all the regularity in the world is available to us. So this is optimal, of course. Federico with Diego did something a lot finer on this. So they went and they actually analyzed how could they get robustness with respect to the multiscale character of the coefficients, okay? So this is not something I did, so I don't feel really comfortable speaking about, but I'm just going to say that there is a much more refined analysis of this method available in Frederic's work, actually, with Diego. Right. So I'm going to present the first set of numerical experiments here. Just remind you, we have divided our domain in polygons, shape regular polygons, and then we have a second level mesh. We have a discretization of the skeleton for the Lagrange multiplier and a second level mesh to solve these local problems here, which are these Neumann problems. And we followed two approaches. First, we make the polygons shrink, right? So we refine the mesh the way we all understand we're refining a mesh. So we call that a mesh-based strategy, which is what I would like to call the H version of this method. The other possibility is you divide once, you leave them, right? And you refine the submeshes, right? So it's like more of a P version, right? So you refine the Lagrange multiplier. When you refine the Lagrange multiplier space, you need to refine the second level mesh as well to be sure that you have your submeshes. So we call that the space-based convergence. And we took a boring example. I'm going to be showing you some more multi-scale things in a couple of minutes, but at least for test convergence, we wanted a proof of concept that this thing works in interesting L-shaped domains. And so we tested both. Let's make these L-shaped domains smaller, or let's fix them and just refine the submeshes. And I hope you can see this. Everything goes to zero as is expected, or better. And this is the point. This is the H1 semi-known. I used quadratic elements for the Lagrange multiplier, cubic elements for the submesh. So we have convergence, which is cubic in the H1 semi-known for the mesh base, for the H version. And we have actually 7 halves. We gain a 1/2 order for the P version, okay? And I apologize if you actually know about P versions. But that's why I'm using really this within inverted commas. And this is something that we observed in every single experiment. We gain 1/2 order of convergence. Yes.
You start with a crazy partition in the beginning, and now you teach us about some refinement. What is the refinement? Would you comment on that?
Yeah, good point. We copy-pasted these patterns.
Copy-paste these patterns?
Yeah, so essentially, you take this square, right? And then you shrink everything and you copy-paste the same pattern times. You cut this in 4, each one of those is meshed like this.
Well, this is a nice illustration, but would you do this in practice?
Yes and no.
Okay, thank you.
It's extremely problem dependent. So, yeah. I'm not going to dwell on that. So what I was saying that essentially we get optimal convergence H2, the right exponent convergence in this refinement, this H version, while the space-based convergence we gain an order, 1/2 order actually, H2 1/2. And actually we observed that at the time when we wrote this paper, that was already quite a few years ago now, and we couldn't explain it, but Frédéric Valentin with Diego Paredes and Théophile Chaumont-Frelais wrote a very nice preprint actually proving that we gained that extra 1/2 order of convergence since actually we wrote this paper. So that's okay. So now I know I read the preprint and as far as I can tell it's correct. We have a proof for the fact that actually leaving the polygons alone and refining the submeshes actually pays off. It bites you differently, of course, because the local problems get bigger and bigger, of course. But it's an interesting result, actually. And we also did a problem like this with inclusions, where it's not really multi-scale, but it's a really, really high contrast problem. So in the blue regions, the DCC is 1, and in the green ones, it's 10 to the power 5. And this is a typical local basis function solution of that local problem, both the elements sharing that edge in there. And this is the reference solution for this problem with, I don't know, several million degrees of freedom. And the one on the right is the MHM solution with 32 Ls, right, with 600 degrees of freedom in the online phase. As we all know, and we heard this morning very clearly explained, the offline phase is a different matter, but actually at least the online phase is 600 degrees of freedom. Okay? And if you are standing in the back and you're falling asleep a little bit, they look very, very similar. Actually, in the eyeball mode, they're okay. Right? So this is what is called the MHM method, and this is at least the part I was involved in the development of this method. So we did the extension to polygonal things, and we refined, we actually sharpened some of the estimates. So that paper is quite technical actually, but in essence is what I showed you. So this, and I'm sure you all have seen problems that look like the ones I was talking to you earlier. Okay, so there are several connections, and as we have been hearing all this week, actually, if we sit down and we compare notes, we'll find connections pretty much between every talk that has been given this week, actually. And that's okay. That means that we're either collectively wrong or we're doing the right thing. Right. So, my favorite connection of this is that this is an extension of the Roy-Artoma basis function. So in the lowest order case, in triangles with constant coefficients, the basis functions that pop up are exactly the Roy-Artoma basis functions. Okay? So that's quite, I mean, if there is no A, and we solve this with P1 and etc., we get, without a submesh, we get the Roy-Artoma basis function. Okay, so this reduces to a very classical case. This is, at least in terms of the local problems to be solved, is similar to the mixed multiscale finite element method that is described in Elchin's book and with Tom Howe. It's actually quite similar. At least in terms of the local problems, this has been breached, properly breached with the multiscale HHO. So this is a paper by Teofil, Frédéric, Daniele Pietro, and Alexandre from, I don't know, 3 or 4 years ago. They essentially proved that in certain cases, this scheme and multiscale HHO lead to the same solutions in certain situations. By transitivity, it can also be linked to multiscale HDG, because HHO and HDG share a lot of common points. This is actually not far away from what Frédéric was talking about the other day as well. The local problems are very similar, actually, or share similarities. At least there are Neumann problems and undetermined problems. And it's kind of a dual approach to multiscale mortar. In multiscale mortar, typically you get the Lagrange multipliers are traces of the function. Here are traces of normal derivatives. And as always, this is not exhaustive. Lists are long and boring, and you always forget somebody. So if I did forget somebody, I apologize. But and one thing I wanted to say earlier is that actually, in there, pretty much what Rob was mentioning the other day about the fact that this is very, very close to the main decomposition strategies. Also, what Axel was describing earlier. So this is very, very much linked. It can be very much interpreted as a domain decomposition problem. Actually. So that's the MHN method. And now I'm going to give 2 extensions. The first one is post-processing. And why do we want to post-process this method? Because there's a very simple reason for it. This exact flux here is an HDiff function. What pops out of the MHM method is not A grad UH. It does not belong to HDiff. It depends on what you want to do with this. If you're okay, if you can live with that, then that's fine. Perfect. You use it, you go home, you live happily ever after. Now, if we are dealing with triangular meshes, and we don't have a submesh, if we just think about this method written, this is your large element, and you don't have a submesh, you have only one Lagrange multiplier here of degree, I don't know, 4, right? And inside, you're solving with degree 7 in only one element, for example. Then what happens is that this guy is the lambda h that comes from here, form a set of conservative fluxes. So you don't know A grad UH on the boundary, this is not in HTIF, but these guys are conservative. So if you are coupling this to a finite volume scheme, you just give this to a finite volume scheme, and you get your transport equation, and that's it, and you go home, right? The problem is when you start dividing this, and then you start losing a little bit of conservation, especially when you introduce submesh. Because then, A grad UH, then your finite volume scheme might be defined in the subjacent triangular, or simplicial triangulation, and then we start getting into trouble, right? So there are two ways we can deal with this. We either take that problem, that local problem, and we solve a mixed local problem, which, don't get me wrong, I love mixed methods as much as the next person, but it's expensive. We make the second level solving more expensive. Or we just lift the Lagrange multipliers in a cheap and local way, very much in the a posteriori fashion. So this is what we're going to do, actually. So we're going to build a Rayard-Thomas lifting. Or, yeah, we will come up with a function that does belong to a Rayard-Thomas place in the submesh. And then we will ask as an added bonus, for free, it will give us an a posteriori estimator. And this is the way we do it. On the boundaries where we know the flux, we build it, we just lift those data, right? So the Lagrange multipliers on the inter-element boundaries here, we just lift those ones by Rayard-Thomas functions, right? Now, in the submesh, in these interior edges, where there are kinks of the solution, we take the average. So the trace of my Rayard-Thomas function is going to be the average of those two gradients. Yes?
What are the conditions on that, this coefficient A at the moment? You write out traces, so you expect more than L infinity. What do you do here?
Well, the integrals need to be well defined.
Okay.
Yeah. And yeah, to prove error estimates we need more, actually. I agree. I did say that. Yeah, I did say that. Right. So I take the gradient, and inside each one of the elements of the local submeshes, I need to preserve a certain amount of moments. Right? And of course, I don't need this if I'm talking about the lowest order possible, but in general, I need to preserve moments up to degree L-1. Remember that L is the degree of the Lagrange multiplier space, okay? And if you look at this set of degrees of freedom, you recognize what I'm doing, right? So what we're doing is that we're mimicking how we define the degrees of freedom for the Rayard-Thomas interpolation. So we take this discrete object, A grad UHH, and we pretty much try to build that pseudo Rayard-Thomas interpolant of that, right? And when we make that remark, proving that this thing converges in optimal, preserves at least the same convergence as the original solution, it becomes, it's not easy, it's fairly technical actually, but the main point is that we were able to prove that this guy is not far off from the Rayard-Thomas interpolant of the original A grad U flux, okay? And actually bounding this is 3/4 of the proof or something more, maybe? Yeah. Right. So, at least by doing this, I didn't destroy the convergence properties of my original method. Okay? There is more, though. We can actually prove that thanks to the fact that the new flux is HTIF, I have this conservation inside each one of the elements. So what this is telling me is that divergence of sigma h minus divergence of A grad U is orthogonal to the space of polynomials of degree L in the submesh. So essentially, in the HTIF norm, up to a projection, what I get is just this orthogonality. So we get essentially a very good convergence because this converges with the submesh. So essentially, this gets almost perfect. We can make it as small as we want. So we can make this thing almost as conservative as we want. Right. So one thing I said earlier, so this is at least the way we build the post-processing and the way we were able to solve the local problems and post-processing things in the right way. Now, I told you that as an added bonus, we got a posteriori estimator, and we do. Unfortunately, and I have to go full disclosure on this, we have to make a technical assumption. It's not hard to fulfill, it's just annoying, because philosophically, everything has been built in such a way that the submeshes in each one of the polygons are independent, right? And this is the dream case scenario. I just put as much effort as I need or as I want in each one of the subdomains. To build the posteriori estimator, I need to impose that the triangulations in two different polygons match on the interfaces. Right? It's annoying. It's not ridiculous. If you think about the fact that many people who do this polygonal finite element methods business, what they do is that they build a very refined mesh and then they agglomerate with metis. It's not crazy, right? You have an underlying extremely microscopic mesh that you just agglomerate, and then you have this structure. So it bothers me, but it doesn't make me lose my sleep. Let me put it that way. But I have to say, we have to be honest about this. But the interesting thing is that if we do that, we can get a fully computable upper bound for the error. So we have a posteriori estimator, which is without constants here, which is essentially the difference between these. And this is very singular zoom. Essentially, we have a gradient, which is discontinuous, and we have a recovery of that gradient, which is continuous, well, HT conforming. The difference is a posteriori estimator. So it's very much based on this term here, which is very singular zoom inspired, plus an estimator taking into consideration the fact that we don't have a conforming solution. So this is just the Oswald operator of the discrete solution. So the Oswald operator is exactly the same discrete solution inside each one of the elements. It only appears in the interfaces because that's where we sacrifice conformity. And the other term is just oscillation, so don't think about that. But the key point is that we have a computable upper bound. And it can be proven locally efficient as well. And this is the work with Larissa, Wesley Pereira, and Frederick. Right, so I told you I was going to show you something a little bit more multiscale. So this is the SPE10 problem. So this is layer 33? 36. Yeah. And so this is the mesh. So again, we were very conservative with our meshes here, so just simply this. And then we see a very good match with a reference solution that was computing with several million degrees of freedom. And
so sorry, what was the right graph showing?
So this is just a cross section of the cross section. Yes, sorry. So we have a good match with the reference solution. Okay. This is the modulus of the A grad UH, right? This is on the reference. This is the MHM method without post-processing. This is the post-processed version. Again, at least in the ideal norm, this looks more connected. It's a little bit more diffusive, of course, because the way we define the post-processing, it sees its neighboring elements on the submesh level at least, but it connects the dots in a way. So it's, and again, the difference between these two guys is a good indicator of the error for the full one. And this is a sequence of adaptive meshes. So the code for this part is written in FreeFem. So what we did was just we put, this is not mesh refinement, this is remeshing. So essentially, don't ask me the technical question how FreeFem does it. I can't remember from the top of my head, but it's essentially there is a solution of an optimization problem that tells you how big the size of the elements around it, and it remeshes, generates Taylor meshes based on local metrics, right? And the good news is that the adaptive mesh seems to be doing the right thing. Okay. Yes.
This is your what we were talking about at the coarse mesh. So on each of them,
yes,
you have your sub mesh and
yes,
your values. Okay.
Precisely. Yeah. Thank you for that. Actually. Okay. And so conclusions of the first part. Trust me, before you get scared, the second part is much shorter. Okay. Am I the only one who's hot here, or?
You can open the door.
Yeah, if you don't mind, actually. Great, thank you. So, what we did in the first part was we extended the MHN method to polyhedral meshes, which is mostly a remark actually, but we sharpened the estimates and we extended also. We're able to break the Lagrange multiplier space. There are several technical things in that paper actually. Since then, several of my collaborators have been working and extending this to elasticity. So Wesley's PhD thesis was on this idea applied to elasticity equations. Convection diffusion. So Diego Paredes has been writing things on convection diffusion and this method as well. And Frederic worked in France for a couple of years, working with Helmholtz and wave equations. Together with Larissa, we have essentially defined a local post-processing technique that is very cheap, which provides us with an HD flux. So that's very nice. And as an added bonus, a fully computable a posteriori error bound that can be also proven to be locally efficient. So what are our next steps is elasticity for this flux reconstruction. So now, in that case, the symmetry of the tensor is going to be a nightmare. I mean, people in elasticity like to have HD conforming tensors, but they also like to have symmetric tensors. And that is something that we yet don't know how to do. So this is going to be fun. And this is just me being pedantic about this. I would love to be able to remove that assumption. So this is probably something that we will have a thought on how to define a posteriori estimators. We don't need this matching assumption on the interfaces. Okay, so let me go back to the last part of the talk, and it's going to be just the last 10 minutes. Where, as I said, I'm going to talk the second M, right? So I'm going to talk about how can we get away from the mixed problem. So, if you remember, for the multiscale hybrid mixed method, the global problem has two unknowns, the Lagrange multipliers on the edges, on the skeleton of the mesh, and one constant element, and it's a saddle point problem. And the local problems are pure Neumann problems. They're constrained, right? So that is essentially, so both things, that's fine, but those things make the problems a little bit slower, right? So the local problems being Neumann, we have to somehow impose that constraint. It's usually slower to solve a pure Neumann problem than a particular one. And of course, it's cheaper to solve an elliptic equation instead of a third point problem. So what we wanted to do when we sat down and thought about this was essentially we want a methodology that allows us to generate elliptic local problems and at the same time, as a result actually, an elliptic global problem only involving the Lagrange multiplier. So what we want to achieve is faster local and global solves. Yeah, what do we want? What do we want? And so this is the main. I'm going to focus on this. I'm just going to focus on redefining the Lagrange multiplier, and then I think I'm going to stop because I just want to convey the one idea. So for this, we go back to the drawing board, and we remember the first step in the derivation, which was multiply by broken H1, integrate by parts, and then this was my Lagrange multiplier. And that led to local Neumann problems. So now we got inspiration from essentially, again, the domain decomposition community, because people picked up on things like this, the additive Schwartz community with non-overlapping domains went from pure Neumann problems to Robin boundary conditions at some point in the 1990s. So we did something that resembles that. It's not exactly the same thing, because what we did here is all of our favorite trick. We added 0. The 0 we added was essentially we added and subtracted this term, where tau is anything in HDiff, right? And now this is my new Lagrange multiplier. It's not just the normal flux, it's the normal flux minus the thing, right? And this is my mixed problem. It looks exactly like the mixed problem we had before for the MHM method, with the very important difference that we have this guy now here. So now, if I build tau, right, in such a way that this local bilinear form is elliptic, I don't have a kernel anymore. So I don't have the one constant per element that I was dragging in the MHM method. And I also have local solves because I don't have this pure Neumann problem again. I have something that looks like a Robin problem. And this is exactly what we did. So we took, the way we built it, there are thousands of choices for tau that do this. We did something very simple. We put our domain in a box. We got the bottom left corner of that box. We built this linear function, which is the position x minus the bottom corner. We multiply it by a parameter nu, which is positive, divided by the number of space dimensions. This is just because we wanted our divergence to be new, okay? Because it looks pretty when the divergence is new and not g times nu, okay? And interestingly, or more than interestingly, fundamentally, if nu is small enough, and this depends on the minimum eigenvalue of my matrix, then we have an elliptic bilinear form. So for a well-chosen nu, that depends on the minimum eigenvalue of the matrix A, we have elliptic bilinear forms. And since we do that, we can do exactly the same static condensation process I told you half an hour ago now, but without having to take care of the kernel. And we end up with a weak formulation that only involves the Lagrange multipliers now. And this guy is given by, it's essentially the same expression as before, with a slightly different t. It's not t anymore, it's this t twiddle that is defined in this way, but this bilinear form here is elliptic. So I don't need to impose zero mean value on the test functions and the unknowns, so this is a problem with a Robin boundary condition. The local kernel is driven by an elliptic bilinear form, and this has in turn, as a consequence, the fact that the global problem is driven by an elliptic bilinear form as well. So by adding zero, adding this appropriate zero, we actually move away from the pure Neumann local problems to a Robin, or something that looks like a problem with a Robin boundary condition, and we get elliptic bilinear forms for both the local and the global problems. This is discretization. I'm going to go very fast on this. Exactly the same conditions that I was talking before. We need the submesh to be fine enough, but nothing that I'm going to tell you now is new, or I'm not going to actually spend too much time on that. This is our global problem. It's completely, it's well posed, of course, because we have an elliptic problem, but interestingly, we have optimal convergence, so we can prove some sort of Sayre's lemma with a constant that doesn't depend on this view. Okay? And this is something I want to stress. The problems, of course, they generate for nu equals to 0. Everything goes out the window if I put nu equals to 0. But until I get to 0, everything, the stability and the convergence are independent of that parameter. Okay? So it's totally robust with respect to this Robin boundary condition, and this is what we did with Tadeu Gomez Santiago Paredes, actually. I'm going to show you just one numerical experiment or two very quickly. This is a problem with a very rapidly varying coefficient here. And this is the reference solution with, I don't know, an overkill of degrees of freedom. And this is the solution of this method. And if you, again, if you are generous, you realize that at least in the ideal norm, these two things look very similar. We were interested in stress testing the robustness with respect to nu, because as I told you, if nu is 0, there's no Robin boundary condition, everything goes out the window. But interestingly, actually, there's a very, very robust behavior until you reach, I don't know, I would never put 10 to the minus 9 as a parameter. I mean, this stalling here is just due to the fact that the condition number of the local problems gets unpleasant, okay? But if you're using something like this, just put 10 to the minus 2 and everything is going to work fine. This is, I wanted faster solves, and we do get a faster solve compared to the MHM method in exactly the same configuration. So this is for the time that we spend solving the local problems, the global problems, pardon me. This is the memory, so we're using less memory. This is for piecewise constant on the edges, quadratics inside. This is for piecewise linears on the edges, cubics inside. And interestingly, we could not solve for the finest configuration. We could not solve the MHM method because we ran out of memory, while by including this Robin boundary condition, we could reach that mesh, right? I'm particularly proud of the fact that it's the first time in my life that I break a cluster. So we were very, very happy with the fact that we could actually push something. I run my codes in this computer, so it was fun to me. Anyway, we also solved again, so this is the permeability for the SPE10 problem. And again, so this is the reference on the right. On the left, this is the mesh. We run the online simulation. Of course, there's the computation of the basis functions underlying, but the solutions look fairly close. And I'm not going to compare the things in the fine. This is a cross-section again, and things work okay. So the conclusions of the second part is essentially by going back to the first step in the derivation of the hybrid formulation, adding the right 0, we moved away from a pure local Neumann problem to compute the basis functions and went to an elliptic case. This removes the local kernel. So by removing the local kernel, it removes the mixed character of the method in the course and partition. Of course, it worked for polyhedral meshes. We also made a couple of points about the error analysis, but I'm getting tired and I guess that you're getting hungry, so I'm not going to give details on that. And it has a good performance. What I really would like to do with this is explore a little bit of a connection with standard Robin boundary conditions. Is there a way to reinterpret this? Because the tau.n doesn't have a sign necessarily. So it's a little bit, it's a little bit more of a complicated Robin boundary condition. And one thing though that I hinted at is the fact that that nu doesn't have an impact on the convergence and the stability of the method, but the algebraic system, the local problems especially, might get really ill-conditioned if you use a tiny, tiny nu. And that's understandable. I mean, you have the stability hinges in that parameter. If that's tiny, you're going to get a very, very bad condition number. On that note, I want to thank you for your attention.